Hello everyone, this is the fifth class of this week. In the first 4 classes we discussed how to analyze truss, 2D truss and then 3D truss, and now we will be doing the similar exercise for beam this week. Okay, so the first example that we take is, but before that recall this is a very most important part in a beam. If you have a beam which is named like this, we have 2 degrees of freedom per node. One is the translation and another one is rotation of the joint. There is no axial deformation because we do have axial deformation in a case of beam, in a case of frame, but for beam we neglect the axial deformation. Okay. Now, this is the general form of the global stiffness matrix. You change the EI for different members and get the different values of the stiffness matrix. Okay. Now, this is important. Now, next is this was the example we considered when we discussed design of we discussed the formulation of design of beam, and this is the solution we already have. We have already solved it and this is the solution for that. So, to start with, we demonstrate the code through example, because for this example we have done exercise manually. So, we will do this for this example, and then we have we'll have another example which is in terms of number of members, it is slightly more than this. Okay. So, let us start with that. So, now this is the code we have for beam. Okay. Now, for this beam, this beam is now okay. So, this was the beam, and this is first this was suppose this is node number 1, this is one node, this is another node. Okay. So, this is say node number 1, this is node number 2, and this is element number 1, this is element number 2, and the degrees of freedom is this is these degrees of freedom is this is 1 and this is 2, 1, 2, this is 3 and 4, and then finally this is 5 and then 6. Okay. While we did manual calculation, probably our degrees of freedom, the numbering of the degrees of freedom were different, but here the reason why we took differently at that time the degrees of freedom, because we wanted, because we saw that if we take the degrees of freedom numbering in such a way that the partitioning of the stiffness matrix will be easier. But here, since we are doing it using a computer code, so you really do not have to bother right now. Now, so these are the coordinates of joints: joint number 1, joint number 2, joint number 3. This, not this one. This is the okay, this one. So, this is joint number 1, joint number 2, and then this is joint number 3. Okay, this was 5 meter if you recall. This was 5. This was okay. This was 5 meter and this was 2.5 meter. Okay, and it is element connectivity. Element number 1 is connected between 1 and 2. Element number 2 is connected between 2, and this is 3. This is 3. Okay. Now, the size of the total degrees of freedom will be 2 into number of node per node we have 2 degrees of freedom. This is total, and now this is the Young E and I, Young's modulus and the second moment of area. Again, for demonstration purpose, we are taking it 1, but you can change the values. Okay. This is a vector, you can change the corresponding values. This is again very similar to the previous one. In terms of structure of the code, it is actually same. This similar. Now, similar means similar to truss. Now, this is the initialization of the stiffness matrix, global stiffness matrix, and the load vector. Now, then fixed end moments. Fixed end moments we did not have in the case of truss, because in the truss, if we know the whatever load acting on the structure, directly from there we can calculate the equivalent joint load. But here, in order to get the equivalent joint load, if you recall, this is one of the very important difference. In a truss, all the forces are acting on the joints. here when we solve it, we solve degrees of freedom solve for unknown at the joints, not at the member, right. But then in truss, which it was very easy because you are solving for the joints and the loads are acting on the joint. But whereas in beam, we want solution at the joint, but the loads are acting on the member. So what we have to do is we have to transfer that member, that load on the member to the joint, and that's why this equivalent joint force, that concept came. So the joint force which will have similar effect, the equivalent effect of the actual structure, okay, when the forces are acting on the member. Okay, in order to get the equivalent joint load, first you have to get the fixed end moments. Fixed end moments is if we assume all the members are fixed, all the beam elements are fixed, and then calculate the corresponding reaction. Those are called fixed end actions, fixed end moments and actions. Now, if we take the first case, the first beam will be, in the first case it is this, and it is subjected to, this is subjected to load, it is subjected to load 12 kilonewton per meter. So, this is 12 kilonewton per meter, 12, and then it is the fixed end moments will be, this is fixed end moment, this is fixed end moment, and this is fixed end reaction, and then this is fixed end reaction. Similarly, for the other one, this one, this is the truss, this is the member, there is no load acting on it. So, this is fixed end moment, fixed end moment, fixed end forces, and fixed end forces. So, since there is no load acting on it, this will be 0, this will be 0, this is 0, and this is 0. We discussed that in one of the classes, but here for the completeness of entire discussion, let us do this exercise. Now, if this length is 5 and this is 12, then this becomes 30 and this become 30, and for a beam with uniformly distributed load, fixed end moments will be WL square by 12, and W is equal to 12, L is equal to 5, and this becomes 25, this becomes 25, and this become 25. Okay. 25. But recall, as per our sign convention, the sign convention is always anti-clockwise taken as positive, and that is why this will become minus 25. Okay. So, these are fixed end moments. So, these fixed end moments we have to give information here. Now, what is the first is the first degrees of freedom associated with translation, vertical translation. This is 30, and then 25 which is clockwise, that is why it is 25, and then again 30 upward direction 30. It is a fixed end moment was clockwise, but as per sign convention anti-clockwise is positive. So, this will be minus 25. This is for member number 1. For member number 2, there is no fixed end moment. So, already we initialize fixed end moments at 0. We do not have to explicitly write it again. Okay, this was fixed end moments. Now, once we have the fixed end moments, next is we have to calculate the equivalent joint load or the nodal load vector. And what is the nodal load vector? Nodal load vector is we get by substituting the equilibrium at different joints. Okay. So, if we substitute the equilibrium at this joint, then what would be the suppose if nodal force this is F1, say nodal force will be F1 plus 30, this 30, that will give me equal to 0 for the equilibrium. So, F1 will be minus 30, right. Similarly, F2 plus 25 will be 0. So, F2 will be minus 25. This exercise has been done here, the equivalent joint load. This is equivalent joint load or the nodal load vector. Okay. This is done, this exercise is performed here. Okay. So, once we have the equivalent joint load, then what next is? So, we have now known and unknown displacement. So, known displacement is, if you look at your this end was fixed, this end was fixed. So, U1 and U2 are known. It is roller support at this joint, at joint number 2. So, U3 is also 0 and it is also roller support here. So, U5 is also 0. So, known displacement will be 1, 2, 3 and 5. So, 1, 2, 3 and 5 are the known displacement, and then unknown displacements are 4, means which is rotation at node number 2 and rotation at node number 3, which is 6. So, 4 and 6 are the unknown displacement. Okay. Now, next is the globalization of, this is the partitioning of the stiffness matrix. Now, this is this is the length of the member and this is the cos theta and sin theta. Now, if you, which is not required for in case of beam, because in the beam always the members, the orientation of the members are with respect to our local coordinate system, but when we come to frame, then we will see that there we need to transform from local coordinate to global coordinate system, and there we need this lambda x and lambda y. Now, this is expression, this is the member stiffness matrix, which is essentially this is the expression for member stiffness matrix, right. Now, here we get the member stiffness matrix, and then one way member stiffness matrix, then we have to take the corresponding element in the member stiffness matrix to get the global stiffness matrix, right, and this will give you the global stiffness matrix. This is the global stiffness matrix. Now, next is, once we have the global stiffness matrix, then we have, and the load vector also we have, then we have to do the same exercise, that P is equal to K into U, and then these we have to partition it, K11, K12, K21, K22, and then this will be U unknown and U known, and this will be P known and P unknown, right. And these P are essentially equivalent joint load or equivalent nodal load vector equivalent joint load. So, this is the partition of the matrix, and this partitioning is done here in this loop. Okay. Now, once we have this part, then we solve for this, solve for K11. So, if we substitute this, that P is equal to K11 into U unknown. So, you solve this for U unknown. So, we get solution of U unknown we get. Now, next is calculation of support reactions. Now, calculation of support reaction in the case of truss, what happened? Truss, we calculated support reaction from the second equation, means Pu, which is unknown forces, that will be K21 into U. That expression gave us the support reactions. Okay. But now, you see, if in the case of beam, this will not be support reaction. This is one part of the support reactions. What we have decomposed, we have divided the structure into two parts. One part is where there is no degrees of freedom, all joints are constrained, okay, which is kinematically determinate structure and subjected to only external load. And the second is there is no external load, all and the structure is only have the deformation. Now, so total reactions will be the reactions from this kinematically determinate structure and the reactions from the structure which has no force, but which has only displacement. So this is contribution, this second contribution, this is the contribution, means the forces generated at the joint because of the displacement, okay, because of the displacement. And then total reactions will be this contribution plus the reactions because of the reaction from the kinematically determinate structure, which are essentially fixed end actions. So total reactions will be total, this is the Pu1. So, Pu2 is the contribution from the displacement, this contribution, and Pu1 it is the contribution from the fixed end action, and the total reaction will be Pu is equal to the first one and the second one, that will be the total reactions. And then finally, it is the globalization of the stiffness, globalization of the load vector. Okay. Now, for this problem we already have the solution. Let us solve it here once again and then see what is the solution. So, the solution is U is equal to 12.5. If you recall, the solution was 12.5 by EI, and minus 6.25 by EI. Here is the solution. And then let us find out support reactions. So, total supports, okay. First let us see the total displacement. So, degrees of freedom 1, 2, 3 are constrained, 4 is theta b, and this is 5 is constant, and the 6 is theta c. And then support reactions are this is the support reactions. Okay, these are support reactions. If you can check the solution that we have with the solution we already obtained. So, this is for this problem. Now, now let us see the second problem. Let us see, these are the solutions already we have. Let us see one more example. This example has, suppose take this example. Take an example like this, where we have suppose we have a 3-span beam, we have a hinge support here and we have a hinge support here. Suppose this is 3 meter, this is 3 meter, and this is 4 meter. Okay. Now, suppose this is subjected to uniformly distributed load as 10 kilonewton per meter, and then suppose this is a concentrated load is say 5 kilonewton at the middle. Okay. And EI is constant for all the member, and let us solve this using this. So, first what we have to do is, first is the numbering. So, numbering will be, we have this is the beam, and these are different nodes. This is one node, another node, another node. So, this is node number 1, node number 2, 3 and 4, and this is element number 1, element number 2 and element number 3. Corresponding degrees of freedom, suppose this is degrees of freedom 1, this is 1, 2, then this is 3, 4, this is then 5, this is 6, this is 7 and this is 8. So, total 8 degrees of freedom it has. Now, in 8 degrees of freedom, what are the information we have? The information we have is, now see at now joint number 1, U1 and U2, these both are unknown. Joint number 7, both are unknown. Joint number 3, only U3 is known, which is 0, and joint number 4, joint number here, it is U5 is only unknown. So, U5 is known. So, then what are the information we have about this joint? Okay. Let us take this. This is also fixed. This is also okay. So, U1, U2 is also your known. Now, okay. So, this is the okay. So, now, okay. Let us remove it. Make it like this. To be okay. So, then U unknown will be U known will be your only U3 and U5, because this is anyway 0, and U unknown, this will be U1, U2 and then U4, then U6 and then U7, U8, these are unknown. Okay. Now, let us see this expression. These are the nodal coordinate, this is the member connectivity, and then this is EI defined. This is now this is your U known is 3 and 5, U unknown is, these are the U unknown. Now, next is we have to give the fixed end moments. Okay. Now, fixed end moments, let us find out fixed end moments. Now, in this case, fixed end moments will be, for the first one, draw the first one, say the first one is this, this is first one, this is second one, this is third one. Now, first one is fixed end moment, this is moment and this is reactions, and this is moment. Now, reactions, anticlockwise moment, reactions and anticlockwise. reactions, moment, reactions and moment. Okay. Now, for the first case there is no load. So, this is 0, 0, 0 and 0, right. For the second case it is a beam, fixed beam which has concentrated load at the midspan, and in that case your this value will be 2.5 and this value will be 2.5, right. Reactions will be 2.5, 2.5 and the moment will be WL by 8. So, this WL by 8 is, this is 1.875, this is 1.875 and this is 1.875, this is minus 1.875. Similarly, here it is WL square by, this load will be 20, this is 20, this is 20, total span length is 4 meter, 20 kilonewton meter per is the intensity, and this will be WL square by 8. And if we substitute WL square by 8, it will be 30.33 and this will be minus 13.33. Okay. So, these are the friction moments. Okay. Now, you look at the friction moments, first is initialized like this, and the second thing is for member number 2, fixed end moments will be, fixed end actions will be 2.5, 8.8, 1.875, 2.5, 1.875, 2.5 and then minus 1.875. Similarly, for member number 3 it is 20, 13.33, 20 minus 13.33. These are the fixed end moments. Now, once we have these fixed end moments, next is then we do not need to give any other information. This is the joint load equivalent load vector, and then boundary condition we have already specified. This is the stiffness matrix and then globalization of the stiffness matrix, solution for unknown displacement once again, and then solution of unknown displacement here, and then finally this is the calculation of support reactions. Again, for support reactions we have two component, one component for the displacement and another component for the coming from the fixed end action. Now, if I do this exercise, so let us run it, and if you run it, then suppose let us first see the displacements are this, the very large value you can see here, that is because of your EI value is taken very small. We will do one exercise where we will just change this EI value and then see what happens here. Now, you see, so these are the displacement and then corresponding support reactions are these. We have just two corresponding, okay, and then PU. Two support reactions, we have just two support here, this is the corresponding reactions, and you can check the equilibrium, whether the equilibrium is being satisfied or not. So, total load acting on the structure was 10 into 40 and then 5, total 45 kilonewton, and this is the total reaction 45 kilonewton. And then final displacement, these are the final displacement, these are the displacement. Now, if you change E, suppose if you change E 10 times, then what happens? Your then or say 100 times if you change, then the displacement will automatically reduce. You see the displacement. Now, one thing, suppose support reactions, if you check the support reactions are this. Next what we do is, next let us make something like this. E1 is this and E2 is it is E1 is this, and then E2 is E2, you make E2 is 1, and then E3 is again 1, E3 is again 1, okay, and then I is SEM, and again if we solve it and then if we calculate the U, you will see that the difference, you can see the difference between these values. Okay. Now this is how you can do this exercise and then check what is the effect of different geometric and material parameter on the final deformation. Okay. So see, then finally once we have the this analysis is not yet complete, because we have calculated only the displacement at the deformed displacement at the node and the support reactions. Other than displacement at the node and support reactions, very similar to truss, we also in the truss we also determine what is the member forces. Here also you have to determine what is the member forces, what is the moment distribution, moment diagram, bending moment diagram, what is the shear force diagram in a member. Now that exercise you can do, but in order to find out bending moment and shear force for a given member, whatever information you need, that information that is already determined, right. For instance, if we know this, for instance, if we have a beam on this, for take the first example, because it was indeterminate beam. It was indeterminate beam, right. This is this was the beam. Now once we know what is the support, what is this, if we draw the free body diagram of this, then on this beam we know what are the loads on it, what are the forces, and what is these forces. So we know this, all this information we know about this beam, we know the support reactions, everything. For this beam, for this member also we know what are the forces, and we also know what are these reactions. So now you take now this is essentially you are dealing with now many statically determinate structure where external load is known and both ends moment and shear is known. Now in order to get you take a section at this, suppose section from X, then you take the bending moment diagram at this section. This will be this is the bending moment diagram at this section, this is the shear force and this is the bending moment, it is mx and this is vx, and then summation of mx is equal to 0, summation of vx is equal to 0 will give you mx is equal to something and vx is equal to something. So you get an expression for vx and mx as a function of x, that you can do it for different members. Okay. So you get the entire bending moment and shear force at a given point. Okay. So this is how we can have a complete solution of the problem. So now what we have discussed so far in this week is, see, the idea here has been, as I said many times, and before closing the week let me repeat that once again. The idea of the entire week has been to tell you that to demonstrate that this method can be translated into a code very easily. It has that ability, and another important thing is the scalability. For demonstration purpose we might have taken very smaller example, but you can do this exercise for very large problem and then see your own that the solution becomes very easy. And now you compare the amount you are spending to solve a structure, or the difficulty you are facing to solve a structure, and if we have to solve the same structure with the methods that you learned in your structural analysis 1, then whether those methods can be applicable the way we can apply these methods. So that was the motivation of the entire course. That was the reason why we had to move beyond structural analysis 1, and this is the reason for that, and this is how we can this is how we have a method which is implementable, translatable, and then which can be translated, and then which is scalable. Now one thing is still left, that is we already discussed frame. One thing is still left, that is 3D analysis of frame, but as I said the same approach you can follow to translate the to write the code for frame, and then again translate that for 3D cases. Okay. So this is for the week. Now next week, if you recall the very first class we mentioned the objective of this course was two. One is, of course, just now we said, moving beyond the structural analysis one, and also another objective is to prepare ourselves for a method which is more general, more widespread method, which is called finite element method. And when we talk about finite element method in the next week, a very brief introduction on finite element method, not the finite element method, the essence of the method. Then we will see that the steps, the concept behind this method is very similar to the matrix method of structural analysis. Matrix method of structural analysis. So, that has also been our objective, to set the platform for a more advanced course, that is on finite element method, for which a very brief introduction we will have in the next week. Okay. So, I stop here today. See you next week. Thank you.